Welcome, everyone. For today's prep, we're going to start to look at series tests. And the test we're going to begin to look at here is the test for divergence. So where we've kind of been so far, we introduced sequences, then we introduced series, and then we looked at a few specific types of series called geometric and p-series. And what we're going to start to do is look at more complicated series. And we want to be able to determine if a series is convergent or divergent. And, well, normally it's kind of difficult to do that directly from the definition using partial sums. So sometimes we can do that. In a few special cases we can do that. But in practice, it's very difficult to do. So instead, we're going to develop a whole bunch of different tests to help us figure this out. And the first one we're going to be looking at, and maybe the easiest one, is this test for divergence. So we're going to see how we can use this to determine if a series is divergent, meaning we can't add up all those terms, essentially. All right, so let's look at what the test says. So, and again, as we're reading through these tests, it's helpful just to keep in mind all the different gadgets that are kind of floating around. So first of all, we have some original sequence. Call it curly bracket a sub n. And then we also have the series that we form from that original sequence. And essentially, this is when we try to add up all the terms. So we'll call that sigma an. So what we're trying to do is we're trying to determine if this series converges or diverges. All right, so the way we use this test is we're going to calculate the limit of our original sequence. So the limit of our original sequence, in some cases, actually gives us information about our series. So what does this say? If we calculate that limit of our original sequence and we don't get 0, so we get something other than 0, or the limit does not exist, well, then our series diverges. If we calculate the limit and we get 0, well, unfortunately then this test is inconclusive. So, kind of write this out as a little flowchart type thing. We're going to calculate the limit of our sequence, of the original sequence here. The limit as n goes to infinity. And really there's a few options. If we calculate this limit and we get 0, well then what this test says is this test doesn't work. It's inconclusive. And by inconclusive, we mean that that's not the end of the story. We're going to have to use some other test. So we'll see the other tests later on. But for right now, the test is inconclusive. We have to try something else. So it doesn't necessarily mean that the series doesn't converge or diverge. It's just we don't know at this point. So we'll have to do something else. So there's really only two options for a series. Does it converge or does it diverge? And when this test is inconclusive, we just have no idea. All right, so the other option is that we calculate the limit and we get something other than 0, or the limit just doesn't exist. Now this actually does give us some information. This tells us that our series, sigma an, diverges. So just remember, we kind of have these two gadgets floating around. We have our original sequence. So this is our list that we're trying to add up all the terms. And the series that's where we try to add up all the terms. So we have our original list. We're trying to add them all up with the series. And the one thing to note, kind of a warning, so it's very easy to kind of misinterpret this test. So of the two options here, neither of them tells us that our series converges. So the test for divergence only tells us if our series is divergent. It doesn't give us convergence. So we can't use this to show that a series converges. We're going to see there's other tests out there that we can use. And again, it's really worth mentioning when we calculate the limit of our original sequence and we get 0, it's really tempting to think that that's going to tell us something about our series. It just doesn't, unfortunately. So when we calculate this limit and we get 0, this test is inconclusive. All right, so let's try an example. Example 1. We have a series here. So when we look at this series is not strictly a p-series. It's not a geometric series. So we're going to try to determine if this is convergent or divergent. And usually the first test we want to consider is this test for divergence because it's kind of one of the quickest tests as well. So the way we're going to do this is we want to get into the habit of just kind of stating the name of the test that we're going to use. So, obviously we're going to use the test for divergence here, but in practice, state the name. And we're going to calculate the limit of just the sequence part of this. So n squared over 3n squared plus 1. And we're going to do the limit as n goes to infinity. Okay. And we're going to see what this limit ultimately is. So when we calculate this limit, n's going to infinity, and the top here is also going to go to infinity. The denominator is going to go to infinity. So this is an infinity over infinity form. So we could use L'Hopital's rule, but it's probably quicker to just use the algebraic approach, where we pick out the largest power of n in the denominator, which in this case is n squared, and then we just divide every single term by n squared. So when we do that, n squared over n squared, big fraction, 3n squared over n squared, plus 1 over n squared. And if we clean that up, simplify it, we end up with 1 over 3 plus 1 over n squared. And this 1 over n squared term, that's a c over infinity form, so that goes to 0. So when we calculate the limit, we end up with 1 over 3 plus 0, which is just 1/3. Make that look a little nicer. All right, so we calculated our limit, and we found that the limit was not 0. It was something other than 0. So what that tells us then is this series diverges. Since the limit of an, as calculated, as n goes to infinity, was 1/3, which did not equal 0. All right, so let's try one more example. And let's look at example 2. So we have this series going from n equals 1 to infinity. The term here is 1 over n. And we want to determine if this is convergent or divergent. So again, let's try out this new test. So let's try our test for divergence. So we're going to calculate the limit of an as n goes to infinity. So let's fill in what the general term of our sequence is. So it's just going to be 1 over n. And as n gets really big, this is a c over infinity form, so this just goes to 0. So our test for divergence here, we calculated the limit of our sequence, we got 0. That means this test is inconclusive. So that's not our answer in this case, but this is what the test for divergence is telling us. It's just inconclusive. So we don't know at this point. Does this converge or diverge? Well, we've actually looked at this series before. This one actually is a p-series, and it's a divergent p-series with p equal to 1. And for p-series diverge when p is less than or equal to 1. So in this case, we have this series that diverges even though our test for divergence gave us this inconclusive result. So we're going to see, in class, we'll see another example like this where the test for divergence is going to be inconclusive, but kind of the opposite happens. The series converges. So we'll save that for class. So we'll see you then. Bye-bye.